We've made pretty good use of classes so far in C++ for mostly what could be described as encapsulation, which is containing data and pairing it with some behavior, and that's a really great use of object-oriented programming. But one of the most powerful uses of object orientation is inheritance, being able to create one type and then to inherit its behavior into a new and extended type. So we'll look at how that inheritance works in C++, and I may make some assumptions that you know a little bit about inheritance, which may or may not be true for folks coming from Python or other backgrounds, but I'll try to do my best to make sure that I bring things back around and review what's necessary. So classes can extend a base class, meaning that you create some base class that may have variables, it may have functions, and those functions may have implementations or not, as we'll see later. Whatever that class has gets inherited into another class if it's used as a base class for that. So here, for example, mammal uses animal as a base class, or in other words, mammal inherits from animal. This is essentially equivalent to if we wrote all of the things that are present in animal inside of mammal, with a few variations there. There are going to be a few differences than if we had just directly copied and pasted those. But if you can see that animal might have some behavior that's common to lots of different other classes, all of those other classes could inherit from animal, and if we needed to make a change to animal behavior, we could do that in one place rather than finding every place that had those similar animal behaviors and changing each of those classes. So the derived class gets all of the base class's members, both functions and data, plus whatever new things, the blue, that we've added inside of the mammal class. Not everything will be inherited, and this is why I say it's a little different than copying and pasting. For example, you will not inherit the constructor, but the base class's constructor will be called before your derived class's constructor. This helps to be able to set up default values for the variables that come from the base class, for example. You don't have to do that in the inheriting class if you don't want to. Some people refer to these as a parent class and a child class, by the way, or superclass and subclass. So it does not inherit the destructor, though the base class's destructor will be called after the derived class's destructor finishes, again, to clean up any of those things that belong to the base class. And the assignment operators, we will have to create our own for the inheriting classes. And friend functions of the base class also can't access things within the derived class. So that would be, again, a little different than if you had copied those over from the parent class and just copied the code into the derived class. The derived class can't access the private items in the base class either, though of course it can use the base class's functions if there are functions that allow someone to get or change those base class variables. So you can explicitly call to the base class's constructor if you'd like to. The default base class constructor will get called if you do nothing. If in your mammal constructor you did not say anything about the animal constructor, it would automatically call the default animal constructor before doing any of the steps of the mammal constructor. But if you had a specific animal constructor you wanted to call, like this one with 2 parameters, you could call to that one. You can do it as a little line up here before you get into the body of your constructor, and I believe you also can do it as the very first thing inside of your mammal constructor. You cannot do any other work before calling to the parent class constructor, though. You have to make it the first thing that you do in there, which can make things a little confusing and complicated sometimes. But it's nice to have that choice between which constructor of the parent class you want to be called. The other thing that people will commonly do in inheriting is overriding the methods of the parent class. What this means is that if the parent class has a method that doesn't actually fit perfectly for the class that's inheriting from that base class, then you can create a method with that same signature in the inheriting class, and it will override the base class's version of that method. We'll see that this varies a little bit in the details of exactly what it does, which may be different for some of you coming from Java. From Java, you override that method, and that will be the one that gets used on, for example, mammal objects here. We'll need to do a little more work in C++. We do need the signature to match exactly, or otherwise it won't be overriding the base class's version. It will be creating a new one that is not going to get treated as overriding that. Just like you can create another function with the same name but different parameters. If you did that here, that's all that would do is create another function with the same name but different parameters and not override. You can explicitly call to the parents method by using the scoping operator like you do in a CPP file. You tell it, I want animals foods function to get called there inside of, say, the mammal foods, or inside of any of your functions in the inheriting class. You could call to one of the animal class functions explicitly this way. If you don't provide the animal : beforehand, it will call to the one that's in your current class, the inheriting class, mammal in this case. So this kind of idea of overriding functions is helpful in another object-oriented concept called polymorphism, where we can have variables of the base class's type and get different behavior based on which inheriting class is actually stored there. For example, in our animal scenario we were presenting before, we had mammals. We might also have mollusks or various other types of animals that inherit from the animal base class. If we create an animal variable and we've made all of those inheriting classes override in the right way different methods, different functions from the animal class, we get different behavior calling a method with the same name on the same variable. So for example, if we changed an animal variable to contain a mollusk at one time, a mammal at another time, and so on, we would get the correct behavior from those. So a pointer to a derived class can be given where a base class pointer or reference is required. In other words, I can create a variable of animal pointer, and I can assign it a mammal. If mollusk inherited from animal, I could assign it a mollusk, or I could assign it any other kind of thing that I wanted to into that animal variable, as long as the class on the right-hand side inherits from animal. I'm allowed to do this. You cannot do it the other way around, in the same sense that if someone says, hand me a shape, you can hand them a square or any shape. But if they said, hand me a square, you cannot hand them just any shape. If someone says, go find me a mammal, you can't just grab any kind of animal. And so you cannot reverse this statement where a mammal variable cannot hold an animal object. But an animal variable can hold a mammal object because mammal is a type of animal. And it's only a type of animal because we inherited from animal. So if you override a function like the foods one that we did a moment ago, and say we wrote a feed function that takes an animal pointer as a parameter, then inside of there, if it calls to foods, by default, when we override like we did before, it will call to the animal one because it's an animal pointer that's being used there. If we want polymorphism, That's not the behavior that we want. We want to be able to have it do the specific feeding that that a mammal needs. It would make no sense to feed a mammal the generic things that are animal foods, and likewise mollusk or whatever other kind of animal that we're looking at. We would want it to be able to feed the specific foods that subtype of animal, that specific animal needs. So we create a mammal, and we could have a call to feed the animal, and we could have a call to feed the mammal. The one calling to feed the animal will, by the way we showed it before, call for foods that belong to animal, not mammal. This one that calls to feed the mammal would do the correct thing for mammal. We'd like it, in spite of whether we specified it as a mammal or not in the variable type, to feed it mammal foods. I would like for my chickens to get chicken food and not some generic thing that somebody determined was animal food. So to do that, to get that polymorphic behavior, where it doesn't matter what the variable type was, we want the specific thing we're looking at today. I want the student who comes to my office to get the help that they need, not the generic help I've decided all students can get. I don't just come up with some pre-made advice for all students and just offer it to every student who walks through my door. I have polymorphic behavior. Students are allowed to come to office hours, and I give help to the specific student that came in through the door. So to do this in C++, we need the base pointer to act as if it was referring to that derived class. We need it to act as if it were a mammal variable when I go to feed the animal that is currently a mammal. We need it to answer the student who's here today even though the variable type was for any generic type of student. The CS415 student that comes into my office needs to get their 415 help, not student help. So to do this in C++, we use the virtual keyword in the base class. This allows us to say this function may be overridden, and if it is overridden, use the derived class, like mammal, use its foods function, not mine. And so we call it virtual, and then in the mammal class, we override that foods function, and that will allow us to use it for animal variables that store currently a mammal. We do not have to say virtual in the mammal class because we're not saying we're overriding this one. We're saying we will possibly override this one in the animal class. And so that gives us basically what's like a pointer to the function or to the method, so that the animal foods function is allowed to point to whatever specific type it's holding right now, to the foods function for whichever specific type it's holding right now, a mammal or a bird or whatever. So when a class has virtual methods, it then builds up this virtual method table. The table will map method names to the actual implementation of the type of object that the variable currently holds. Each class instance has a pointer to the appropriate table for its class. So you can see that all of these different objects here may have been instruments, and they all map to the specific functions that they are able to use. And then an instrument variable then, for example, would be able to play the way that the specific instrument you have in your hand right now plays. That's polymorphism. We can, if we don't have a good implementation of what shelter is for an animal, for example, if there's not a good generic way to define it in the base class, but we want that polymorphism where lots of different animals will require shelter, then we define it to be pure virtual. We give it no implementation, and we set it to 0. We define it virtual, we set it to 0 rather than giving it implementation, and that sets the pointer in the virtual method table to 0, and allows us to reference, again, those ones that are specific to the subtypes, the deriving classes, the inheriting classes. You can't give a definition for this method in the base class, and often we choose this option because it doesn't make sense to give a definition for this method in the base class. A common example I give is shapes. Circles have a function to calculate area. Squares have a function to calculate area, but shapes as a general concept don't necessarily have a function to calculate area. And so it doesn't make sense to write an area function for your shape class. You would define it to be purely virtual and never give it a definition, just to make a placeholder to know that all shapes will calculate area. We just don't know how until we have a specific shape in our hand. The trick with this is it makes it so that you now cannot instantiate the base class. You will never create an animal object. You may create animal variables, but you will never be able to create an animal object if it has virtual functions. Because of course, to create an object, I should then be able to call all of its functions. Since this function has no definition and is purely virtual, I wouldn't be able to call it, and that would make my program very dangerous if I tried to create an animal object, and then I've told you it has a shelter function, but there is no definition of that shelter function. This would not be clean ways of writing objects in code. You therefore can use those base type pointers to refer to the inheriting types, the subtypes, to get this polymorphic behavior. If you're familiar with interfaces in Java or in other languages, C++ doesn't have a clear keyword for defining an interface. An interface in Java is basically a class that has only pure virtual functions. They have no implementations. So in C++, we can get the same behavior as an interface from Java by creating a class with only pure virtual methods. It has no real methods of its own. And it has no data members as well to, again, behave like a Java interface. And then that means that you would probably not have a CPP file because you only really need the header for it. You can, if you want to, create classes that have a mixture of pure virtual and defined functions. In the shape example, for instance, we might define that all shapes have a name to their type and that there might be some toString method for shapes that prints out or that returns their name. Those might be things that would be reasonable. You, again, don't know what the value for the name is going to be, but in the constructor of circle, you could define name to be circle and so on, and know that if I turned it into a string, I would get the word circle. So there's plenty of times where you might define some of the behavior in the base class and leave some of the behavior pure virtual to only be defined in the inheriting classes. But often in Java, we stuck with interfaces as these pure virtual, no definitions for any of the functions. You can still do that in C++. You just have to do it yourself by making every function pure virtual with no definition. This provides essentially a sort of contract through the base class of saying all animals will have these sets of functions. I don't know what any of them do in detail until you tell me what kind of animal you're dealing with, but all animals will definitely have these. That's the kind of thing that you're stating by a virtual function, or a pure virtual function, or by, in particular, an interface-like class that has only pure virtual functions. So much like in Java, if you've created this interface-like class that has only pure virtual functions, then to implement that interface to derive from that base class, you would derive from it and you would override all of its pure virtual functions to provide the backup, the keeping the promise of the interface that you would have all of those methods which you gave only signatures for before. So that gives us a little bit of an outline of how inheritance looks in C++. Some thought on this question of polymorphism, getting one variable type of the base type and putting into it those inheriting types, those subtypes, objects of those different types, and therefore that same variable can give us different behavior specific to the type of object that it's storing right now. And we can get that by making virtual functions, and if we don't know a good implementation that is generic to all of the types that are going to inherit from our base type, we should make those abstract by writing pure virtual functions, and we can even go all in and create something that looks like a Java interface.